Well, we're going to spend the day today talking about clouds, and we started this last time. So I'll do a little bit of review. And it's all PowerPoint today, which can be fairly boring, so I hope you will shout out questions as we go through this material. So just remember, the subject today, and we started last time, is clouds and other occurrences of condensed water in the atmosphere. So it's all about water in the atmosphere today. We talked about it being a water planet, but not only in the oceans, but in the atmosphere as well. Both water vapor, which is invisible, and the clouds that form when water vapor condenses. We went through these definitions. I won't repeat that unless there are questions. Are there any questions on these definitions? You've had a couple days to look at those. Question, yes?
I have a quick question whether this PowerPoint is uploaded on the class.
It's already there. I loaded it this morning about an hour ago. Yeah, it's already there. A PDF version of it, yep. Any questions on these definitions? These are really important. You can't get away without knowing these 6 quantities. And these as well. But I'll be saying more about this as we go through the lecture, but these are really important terms. I didn't show this last time, but I should have. It's a plot of saturation vapor pressure for water. It just says vapor pressure, but it should say saturation vapor pressure as a function of temperature. Saturation vapor pressure is defined as there's two equivalent definitions. I like them both. It's the partial pressure of water vapor in equilibrium with a condensed phase. In other words, if you have a chamber that has some liquid water in it and at a certain temperature, and you wait for a while, there will be enough evaporation off the surface and the void will get filled with water vapor. And if you wait long enough, the partial pressure of water vapor in that chamber will come to the value given by this curve, depending on the temperature of the system. So the higher the temperature, the more water vapor will evaporate, and the higher the water vapor partial pressure you will have in the chamber. Now here's a curious thing. It actually doesn't matter whether there's air in the chamber above that liquid water or not, because this is a property of the water, not of the air. And I'll often mistakenly say things like, well, the air is saturated. That's not quite right, because it's the water vapor we're talking about. Now, it's interesting that water is mixed into air, but the air is not really controlling this. This is a property of water alone. You'd have the same partial pressure of water vapor above a liquid at a certain temperature, whether there was air there or not. Of course, if there was air there, the total pressure would be higher, but the partial pressure of water vapor would be the same value here. Yes?
What is the difference between saturation vapor pressure and regular vapor pressure?
Well, the vapor pressure is what you have. Depends on how much water vapor you have and its temperature. But the saturation is the value of that quantity that you would have when there's a condensed phase present and they've reached equilibrium. Or another way to put it is that the saturation vapor pressure is the maximum you can have before condensation begins. In other words, at a certain temperature, let's say 20 degrees Celsius, if I had a vapor pressure of 1 millibar, that is less than the saturation curve, so nothing's going to condense. However, I could bring the air to I just said it again. I could bring the water vapor to saturation either by adding water vapor to that chamber in some way or by cooling it. In either case, I can approach the saturation curve, and when I get there, whether it's there or there, it doesn't matter, when I get there, the humidity, the relative humidity will be 100%, And if I try to go beyond, using either mechanism, the excess water vapor will condense out to form liquid or ice. So the relative humidity is less than 100% here. When you push it to saturation, no matter how you do it, either by adding water or by cooling, and go beyond, then you'll get condensed water. So that's the key idea there. And I mentioned this last time. So there, to approach saturation, you can add moisture. That moves you up on that diagram. Or you can drop the temperature. And there's two common ways that the temperature could be dropped in an atmospheric system. One would be cool it by removing heat. Put that little piece of air next to something cold, and so the heat is drawn out of it by conduction. And that leads to something we call radiation fog. I'll give you examples, and advection fog also. Or you could cool that parcel of air by adiabatic expansion. That means lifting it. You don't have to put it in contact with a cold surface, just lift it. And it'll expand as it goes to lower pressure and cool itself by the fact that it's doing work on the environment. That'll drop the temperature, and again, you'll push towards saturation, and if you go beyond, a cloud will form. So these are the three ways that you approach saturation, and I'm going to give you lots of examples of these today, and stop me if you have questions. We did these first few last time. Sea smoke is where you have a warm water surface and cold air. You evaporate water off the warm surface into the air, but the air can't hold that much water vapor, so you start to get little liquid droplets forming from the excess water vapor, the amount that you've pushed beyond the saturation value. And this one we talked about last time, contrails. You're burning hydrocarbon fuels. Byproduct of the burning is carbon dioxide and water vapor. So you've added water vapor to the air. You've pushed it beyond saturation. The excess will condense out in tiny water droplets. Remember, the vapor itself is invisible. There's vapor everywhere here. You only see the condensed particles, either liquid or ice. Contrails. We talked about this. I think we did. Nuclear plants have cooling towers to get rid of heat that's come out of the back side of the turbines. And what they do is just to evaporate large amounts of water, put it up in the atmosphere, but as soon as that very humid air reaches the colder environmental atmosphere, it condenses because you've added water vapor, it can't be held, and the excess goes into liquid droplets. When you breathe out on a cold winter day, you're doing exactly the same thing. Okay, now radiation fog is an example of how we're going to cool the air off, ultimately causing fog. And the way you do that is usually to have a clear night, no clouds above, so the infrared radiation from the Earth's surface can escape very handily. Maybe a good half of it escapes to space, which cools the surface of the Earth down several degrees overnight. The air right in contact with that Earth's surface then is going to lose heat by conduction to the cold surface. When you lose heat, you drop the saturation vapor pressure. You're not necessarily changing the amount of water vapor in the air, but you're changing the amount that can be held in the vapor state. And therefore, the fog forms first for the air that's right in contact with that cooling surface. That's called radiation fog. The word radiation goes back to how the heat has been lost from the system. But thermodynamically, it's similar to cases we've already spoken about. And this is a common thing to see, especially in valleys, because in slightly mountainous terrain, the air that's been cooled by contact with the surface will tend to run downhill and collect in the valleys. So you can get radiation fog in flat terrain. I've seen it many times, but I've seen it even more frequently in slightly hilly country where the cold air runs down into the valley and the fog is found most dense, most thick down in that valley. But it's still radiation fog. Notice the clear sky above, which is usually when you get a good strong case of radiation fog, it's because there's no clouds above overnight. Advection fog is a little different. There, a surface was cold to begin with, and then you brought in moist air by the winds over that surface. Once you've moved the warm air over the surface, it loses heat by conduction again, and the saturation vapor pressure drops, the relative humidity exceeds 100%, and the fog forms. So the only difference here is how you generated the cooling. Instead of doing it by radiation, you did it by moving warm, moist air over a colder surface. This is quite common in areas of the world ocean where you have a cold ocean current. For example, the California current that comes down along the coast of California is a cold current, and when warm air masses move over that, whether it's from further west in the Pacific or whether it comes off the land, suddenly that air is going to lose heat to the cold water beneath. Remember, this is not sea smoke. Sea smoke was the opposite. This is cold water, warm air. Remember, sea smoke was just the opposite of that. Here, you're not gaining water from the ocean, you're losing heat to the ocean and causing the fog to form in that way. Here's another example of advection fog along a coastline. It's quite common, for example, north of here, up in the Gulf of Maine, and further up around Nova Scotia where the Labrador Current comes down, the cold Labrador Current. It's very common. In fact, you might have advection fog 2/3 of the time. You might have advection fog over that cold flowing Labrador Current because of this effect. No matter what direction the wind blows in from, it's probably warmer than that Labrador Current, so it's going to lose heat to it, and the fog is going to form. So it's a very foggy area up there where there's a cold ocean current. Questions here? Maybe you've seen this. Okay, now we're going to talk about clouds, which is the primary subject of the lecture. Clouds are formed by rising air, and the thermodynamic mechanism is adiabatic cooling as air rises. As the air gets cooler, as its temperature drops, the saturation vapor pressure drops, and you will reach a humidity of 100% and then perhaps beyond. And if you try to go beyond, the excess water vapor will immediately condense out to form a cloud. So we're going to take a look at a few types of clouds, but in all cases, the thermodynamics is the same. So here is our friend, the fair weather cumulus cloud with the flat base, the cauliflower turbulent tops, and probably the most common type of cloud. And I have a little time-lapse movie. We did a project in my group a few months ago down in the Caribbean looking at how clouds and precipitation are generated in the tropical belt of our planet. We flew aircraft through clouds and so on. And if I can get this to work, I'm going to show you some time-lapse photography of cumulus clouds over the island of Dominica. The sun just rose. That black to illuminated thing was the sun rising in the east. And you're beginning to see cumulus clouds forming here, bubbling up, almost like boiling in some sense. But this is heat from the land rising, but then as the air rises, it cools. The humidity exceeds 100% and the cloud forms. But then the air rises into the clouds and spreads out and descends. So maybe you can see it, but clouds are also disappearing. As fast as they're being produced in the updrafts, they're being eliminated by the downdrafts, because this adiabatic cooling and heating is a reversible process. You cool when you lift, you warm when you descend, and so you're going to form cumulus clouds, and the parcels are just moving through these things. Cloudy on the way up and clear air on the way down. The time is in the upper box in local time, so now it's evening, and just before the sunset, when the heating of the island was reduced, so was the convection. So this was driven by the sun heating the island, the warm air rising, but then in the rising process, the water vapor became saturated, condensed, and the cloud was formed. Any questions on that short video? When you are looking at cumulus clouds yourself, you normally see a fixed pattern. You may have noticed, well, it's still here, in fact, the speed-up ratio on that time-lapse photography was 720. That's a big speed-up ratio, right? So things are happening in this time-lapse film 700 times faster than they do in nature. But that makes it wonderful because you can see the process happening. When you look at it yourself, you see a static cloud pattern, and if you try to watch it, sometimes you can see the changes, but it's hard because they're slow based on the human time scale. You have to have a great deal of attention focused on that cloud to be able to watch it evolve and change over a period of an hour or two, whereas with time-lapse, we see it all before us happening, and we can easily understand it. I wanted to give you a couple other examples of what we did in this project. Here, for example, is a short aircraft flight through a couple of those cumulus clouds. And the aircraft is equipped with all kinds of wonderful instruments on board. But let me just show you what's plotted here. So this is a horizontal distance in kilometers. So the airplane flew about 30 kilometers and passed through, depending how you count them, 2 or 4 different clouds, maybe 1, 2, 3, 4, something like that. What's plotted in blue, LWC, is the liquid water concentration. In those cloud drops, how much total liquid is there in units of grams of water, liquid water, per cubic meter of air? We have instruments on board the aircraft that can measure this. And so when it's 0, of course, you're not in a cloud. A cloud is defined by its liquid water content. If there's no liquid water, you are not in a cloud. So we entered the cloud there. We had values of 1 to 2 grams per cubic meter of liquid. Then we're briefly out of the cloud, back into another one, out, in, and finally out. Here's the vertical motion. The air is moving up and down. So not much vertical motion outside the cloud, but inside the cloud, it's noisy, it's turbulent. But most of the motions are upwards. Okay, there are a few little downbursts, but generally, most of the air inside a cloud is moving upwards, as I argued it must be, because it's adiabatic cooling that is responsible for the cloud. Here is the water vapor mixing ratio. We call that the specific humidity. It's in units of grams of water vapor per kilogram of air. How much water is mixed into the air? It was 11 outside the cloud and about 13 inside the cloud. And then we also had instruments that could measure the droplet diameter of the cloud droplets. And they're ranging between about 16 and 28 microns. A micron is a millionth of a meter. These are small droplets, so small. This is a typical cloud droplet. They're so small that they don't really fall out very much. They just follow the air. They're so tiny that their gravitational acceleration is quite small, and they mostly just follow the air parcels. But you can measure them as you fly through a cloud. So that gives you an idea of that. And then one more diagram from the same experiment we did. We found that under certain conditions, some clouds would have, the cloud droplet diameter would be larger, in other cases smaller. This is the probability density of finding a particular cloud droplet diameter. On one research flight 13, we found cloud droplets that were on the order of 20 to 25 microns. On another day, more like 10 to 15. And that has a lot to do with then whether it's going to rain or not, because in order to produce rain, well, let me just remind you of something. A raindrop is about 100 times larger than a cloud droplet. 100 times. The diameter has a ratio of about 100 times. In order to make a raindrop, you have to bring together a very large number of cloud droplets. How many would you guess? How many do you have to bring together to form one raindrop? Oh, I thought you were going to say that. Remember, I said the diameters had a ratio of 100 to 1, but it's really volumes we're talking about. In order to construct a raindrop, you're going to have to bring together the volume of a raindrop. So how many droplets of 100 times smaller do you have to bring together to form the volume of a raindrop? 100 cubed, right. That is to say 10 to the 6th, or a million. You've got to bring together a million of these to make one raindrop. Please remember that, because one of the longest questions in all of meteorology goes back to the days of the Greeks is, why do most clouds not rain? But a few do. In some cases, there's a mechanism that can bring together a million cloud droplets to form one raindrop. But it depends to some extent on how the cloud droplets, how big they are to begin with, and we found some variability from case to case in that cloud droplet size. Again, the units here are microns. These are the small ones. These are the cloud droplets, the ones that just hang up there in the sky. Any questions here? Okay, now let's look at some other cloud types. I'm not going to go through this exhaustively. This is a type of cloud that is called, in the scientific literature, it's called altocumulus, meaning alto meaning mid-level cloud, about halfway up through the troposphere, and cumulus because it has some turbulent structure to it. This particular type of altocumulus, which has a kind of banded nature to it, is called colloquially mackerel sky. And you find that term very often in the literature of the sea, for example, but you find it commonly in other types of literature as well. Now, you know what's going on here. Well, you don't know everything, but you know that the air is rising there and sinking there, right? Rising to give you the cloud, sinking to give you the clear air. You don't necessarily know what's causing that particular pattern of rising and sinking air. I think it has to do a little bit with wind shear and maybe a little bit with cooling of the tops by radiation, but I'm not sure in this case. But I do know that that's an altocumulus cloud of the type that is commonly referred to as mackerel sky. And where does the word mackerel come from, you may be asking? Well, the fishermen that gave that cloud its colloquial name were catching Atlantic mackerel, and that pattern on the back of the fish reminded them of that pattern. So it's not the scientific name, but it's a common colloquial name for that kind of cloud pattern. This is cirrostratus. So what does that mean? Cirro means high ice cloud. Stratus means without structure, horizontal, a fairly homogeneous horizontal layer of cloud. So, okay, you see a little bit of light and dark patterns, but generally that is a layer of rather contiguous cloud. It's a little bit filmy, which reminds you that it's probably ice, and if it's ice, it's certainly high. It's certainly up in the upper part of the troposphere. Here's a fair weather cumulus that is beginning to develop vertically. There's enough latent heat being given off when the water vapor is condensing, and that heat is keeping the cloudy air warm enough so it's not just stopping, giving you a fair weather cumulus and then the air descending again. Instead, it's continued to rise. I don't believe it's hit the tropopause yet, so I'm going to call that, and it's not raining out the bottom, so I'm going to call that cumulus congestus, a growing cumulus cloud. But now, here's one that is raining out the bottom. You see it here. I don't see a good anvil yet, but because it's raining and nimbus means rain, I would definitely call that cumulonimbus. It's a cumulus cloud that's raining, and typically these are deep. They go from 1 kilometer for the base up to 8, 10, 12 kilometers at the top. So that's a deep cloud spanning the entire troposphere from bottom to top. Question?
So could you explain again, like what causes, like what about the latent heat causes it to keep on rising?
So remember, we talked about it. We defined a stable atmosphere as an atmosphere where a rising parcel finds itself colder than its environment, more dense, and wants to fall back. Well, that might happen in this environment in the dry air, but inside the cloud, that air parcel has another source of heat. As it rises, water vapor is condensing, adding heat to the air parcel, making it warmer, and that allows it to continue to rise. So we would call that a moist, unstable atmosphere, where due to that extra latent heat, the parcel is able to rise and form that cloud.
So when it condenses, heat is given off.
Heat is given off, right, exactly. Here's another cumulonimbus. Now, the bottom of it is obscured by other clouds, so I've taken a bit of a risk in calling it nimbus because I can't see the rain coming out the bottom, but I can see the anvil. That air has risen, hit the stable stratosphere, and spread out a little bit in the shape of a blacksmith's anvil, so we call it an anvil. And usually, by the time it's done that, there is rain coming out of the bottom. So I'm going to take a chance and call that one also cumulonimbus. It's probably going to have liquid water down here, probably some ice at the top. Sometimes underneath the anvil, you get a rather famous and interesting cloud structure called mammatus. Air that's been carried up to the tropopause and spread out because it can't rise any further, then begins to descend again in lumps. And when the lighting is correct, as it was here, when the sun is low in the sky and is illuminating these things kind of from the side, they take a rather dramatic appearance of smooth, descending blobs of cloudy air coming out of the bottom of the anvil. It's called mammatus. The origin is, I think, evident. My favorite cloud is the lenticular cloud. When air is forced to rise over a mountain range, it's lifted temporarily and then sinks on the back side. And when it's lifted, it'll reach the saturation point, perhaps. Cloud will form, but then as that air descends back down the lee side of the mountain, everything reverses, and the excess water will evaporate, and you get back to clear sky. So we're only seeing half of it here, but this is a case looking northwest from a point that is east of the Sierra Nevada range. So the air is rising here, forming that cloud, and we don't see the other side of it here. The remarkable thing is, though, that cloud stays more or less steady as the air continues to flow through it. So the cloud is fixed, but new air parcels are entering and leaving, entering and leaving, entering and leaving, and the cloud just stays there more or less in the same place. You may see it wiggle around a little bit, but generally it just stays there. Remarkable to see. Here's one over Mount Fuji, lenticular cloud, and sometimes it's even hard to know which way the air is blowing. I think the air is from left to right here. It's rising, a cloud is forming. Then when the air descends, that condensed water evaporates again, and the parcel goes back to just clear air, water vapor only, no condensed water. These occur in a variety of different configurations. I like this one. This is called the pile of plates lenticular. And now why does it look like this? There's one mountain range. The air is rising up over it and then sinking. Why that structure? Well, that structure can only be there. I've thought about this for years. There's only one possible explanation that I've come up with, and that is that the water vapor upwind of this region was layered a little bit. A moist layer, dry layer, moist layer, dry layer, moist, dry, moist, dry. Then when the whole thing was lifted, the moist layers came to saturation. The dry layers, with roughly the same amount of lifting, did not. And so the moist layers formed a cloud, the dry layers form the interleaving dry air, and then of course when the air descends back down the lee side, all the condensed water re-evaporates. These things are sometimes found right, almost connected with the mountain range as you see them there, but sometimes they're quite some distance above or even displaced from the mountain, in which case they have been very frequently identified as UFOs, unidentified flying objects. In fact, a very large fraction of the UFO reports over the last 100 years can ultimately be explained in terms of lenticular clouds. So be skeptical of the UFOs, and the first place I would look for an explanation of a new sighting would be to see if it's in a mountainous area, see if the atmospheric conditions were right to form this kind of local smooth uplift, more or less stationary because of the way this cloud is formed. Now, that covers most of the clouds, but I wanted to be sure your background was a little bit broader than this. So I want to talk about vortices for a minute. Oh, question, yes?
You said that there was like a right atmospheric condition to form those lenticular clouds. Like what is that?
Well, if the air was too dry to begin with, and you only lifted it a few hundred meters, you wouldn't bring it to saturation. It wouldn't be enough.
So it has to be humid.
It's got to be humid enough, at least in those layers, and the mountain's got to be high enough to lift it to saturation. If you don't bring it to saturation, then you won't get the cloud forming. Anything else on these clouds? So vortices. Now, intense vortices, no matter how they're formed, have low pressure in the middle. If you don't believe this, take a bucket of water and reach in with your hand and get it swirling very fast, and you will notice that the surface of the water in the middle is drawn down in the middle. You can do it with a glass of water too at lunch. Just get it swirling and you'll see that in the middle the water is drawn down. Hydrostatically, that tells you there's lower pressure in the middle of the vortex. It has to be that way in order for centrifugal force to be balanced by a pressure gradient force in that. But that's not our primary focus. So if you accept the fact that there's low pressure in the middle of a vortex, if you take an air parcel that has a certain amount of water vapor in it, and you move it into the center of that vortex somehow, its pressure will drop. Well, what happens when you drop the pressure of air? It expands, and it cools by adiabatic expansion. So until this moment, I've been talking about adiabatic expansion as if the only way you can do it is by lifting air into lower pressure regions. But here's another way you can do it. Just by taking a parcel of air from outside and putting it inside a vortex, you can drop its pressure. You can make it expand adiabatically, drop the temperature, drop the saturation. The whole story continues, is the same. You drop the saturation vapor pressure and a cloud can form. So a tornado, this part of a tornado is called the condensation funnel. Now, sometimes another funnel is identified near the bottom, and you can begin to see evidence of it here, the dark region. That's called the debris funnel. That's material that's been kicked up off the surface and is being carried upwards. I'm not talking about that one. I'm talking about this actually much more spectacular funnel. That is just a cloud. That's just condensed water vapor to form cloud droplets because air from out here is getting into there and there's low pressure in the middle. So that's just another example of adiabatic expansion causing a cloud to form. In this case, the condensation funnel of a tornado. Questions on that? We'll talk more about tornadoes later in the course. Now, pretend you didn't look at that for a moment. And as you first looked at that image, you may say, well, he already showed us that, didn't he? He showed us contrails earlier in the day, but take a closer look at that airplane and where the vortices are coming from. These, not the vortices, these little cloud lines, they're not coming from the engines. Actually, they're coming, in this case, they're coming from the ends of the flaps. That pilot he's got his landing gear down. He's got his flaps down to get extra lift. And he's producing little wingtip vortices, not exactly off the wingtip, but off the edge of the flaps. That's a trailing vortex. There's low pressure inside, and the low pressure is causing some water vapor to condense to form cloud droplets inside that trailing vortex. So be sure you can distinguish that from the contrails. Yes?
How does that create a low pressure?
Well, you know, in order for an aircraft to fly, it has to have fast air moving over the top of the wing, which by Bernoulli's law gives you low pressure, and higher pressure at the bottom. Near the end of that wing, because you have high pressure and low pressure, the high pressure air whips around and forms a trailing vortex that comes off the wingtip. But remember, just like the tornado, the fact that there's swirling air in that ensures that there's going to be lower pressure in the middle than there is outside.
So how common is this?
Well, again, the humidity has to be high in order for that little bit of pressure drop. So I'd say a picture like this is relatively rare, because you probably would have to have humidity higher than 95% pre-existing in order to get that kind of a phenomenon. Okay. There's another way to get a sudden drop in pressure, and this is off of an aircraft flying supersonically. It's flying very rapidly through the atmosphere, faster than the speed of sound. It has its own characteristic flow field around the aircraft when it's flying that fast, and its own characteristic pressure anomalies. Normally, a supersonic aircraft, where it parts the air, gets high pressure, and where the air is coming back again near the rear of the aircraft, you're getting lower pressure, even lower than ambient. Even lower than ambient. And we will see what this does to the thermodynamics of the air. Air entering that lower pressure region on the back of the aircraft will adiabatically expand, and so on, and a cloud will form. The same procedure we've talked about. Let's take a look at what that looks like. How many have seen that kind of diagram before? Only a few of you. I am intrigued by this, partly as a pilot, but mostly just for the beauty and the wonder of that. Your first thought may be, well, there is something there and the aircraft is just flying through it, like some kind of a membrane or something, and the aircraft is... No. The aircraft is flying supersonically, perhaps 1,000 miles per hour, and this is moving along with it, exactly following it, exactly tied to it. Notice there's another one, little one, just behind the cockpit. There's a little bit of a low pressure area there and a bigger low pressure area there on the rear of the aircraft, and the air parcels, which were subsaturated here, have entered this low pressure area, and the story is the same: adiabatic expansion, cloud formation. And then when you get beyond that, the pressure jumps up again, the process reverses, and the cloud disappears. Question in the back.
Can you distinguish what's the difference between adiabatic cooling and adiabatic expansion?
Adiabatic expansion is, they're almost the same thing. When you have adiabatic expansion, you get adiabatic cooling. Adiabatic expansion is defined as expanding air without adding heat. The word adiabatic means without adding heat. When you do that, when you expand air without adding heat, you cool it by the work that it does on its environment. In other words, you drop the temperature. So those are almost synonymous, but one leads to the other. Does that help? And then one more example of this. I call that the fighter plane wearing a tutu picture. And again, this is moving with that aircraft. Now, this is not so common because the humidity probably has to be something like 95, 96, 97% in order to get that phenomena to occur when the aircraft flies through it. So,
Isn't that at a higher altitude?
not necessarily. And it could be at any altitude, but the relative humidity would have to be high to begin with, the relative humidity. Questions on this? Haze and pollution. We talked about this a little bit. If the air is polluted and the particles are hygroscopic, that is, they like to attract water, then even if the relative humidity is less than 100%, they may attract a little bit of water onto them and make themselves bigger. And when they do that, it's called haze, and it reduces the visual range. Take a look at this photo. Here's a nearby forest. There's a forest on a somewhat more distant hill, and forest on an even more distant hill. This is up in Maine, I think, one of my summer vacations. And those three surfaces are pretty much identical, and yet that looks lighter and bluer than this, and this looks lighter and bluer than that. What's happening is that there's haze in the air, and sunlight is being scattered by that haze to your eye. So the further away the object is, further away the object is, it's not the darker that it looks, the lighter it looks, because you're adding what I call path radiance to that, to what you're seeing. And of course, as the air becomes more and more humid, those particles will grow a little bit more. That mountain may disappear. That mountain may come to look like that mountain. And so this can be sometimes, of course, you need the particles, but the humidity plays a role as well by how much water condenses onto those haze particles. Clouds seen from space. These are some fair weather cumulus clouds over central South America, equatorial South America, near the Ucayali River. They're just fair weather cumulus clouds, but they're forming in rows. Those are called cloud streets in the literature. And they are just fair weather cumulus clouds caused by the heating of the ground by the sun. But if there's a wind blowing, cumulus clouds tend to line up in rows, or we use the word streets. And so I know from this image that the wind is blowing either in that direction or in that direction, because clouds line up with the wind to form that kind of a pattern. If I were to guess, I'd suspect it's from upper left to lower right, but I know it's always parallel to the wind in that case. This is hard to see sometimes from the ground because you may see a cloud over there and a cloud over there, but it's hard to make out this pattern because you're too close to it. Being up in a satellite, you get to see the whole pattern. And of course, that's really true for larger scale cloud patterns like this. Here's North America. Here's a beautiful mid-latitude cyclone. The cyclone center is here, occluded front, back to here, warm front, cold front. Now, if you're at any location, all you see is overcast or clear. But from far enough away, from up in space, you can see this is part of a beautiful, we call that a comma cloud because it has the shape of a comma, but that's a beautiful indication of what's called a mid-latitude frontal cyclone. And we'll be talking about the structure of these later on in the course. Thunderstorms look like this from space. They have an anvil. We've spoken about that. That's kind of a flat part where it's hit the tropopause and can't go any higher, so it spreads out. And the main updraft is usually where this bumpy part is. The main updraft is there and hits, spreads out, and then forms a big anvil. Hurricane looks like this. There's the eye of the hurricane, rising air, big anvil spiraling outwards, clear sky, some scattered cumulus other places, but again, you need to be on a satellite to see that big pattern there. We're almost done, but I want to remind you that we're talking about clouds, we're talking about liquid and or ice. It's the condensed phase of water, but it could be liquid and or ice. If the temperature is higher than 0 degrees Celsius, it's always going to be liquid. If the temperature is colder than minus 40 Celsius, it's always going to be ice. But if it's in this intermediate range, this rather wide intermediate range of 0 Celsius down to minus 40, it could be either liquid or ice. If it's liquid, we call it supercooled liquid because it is below its normal freezing point. There's a definition. It's very dangerous for ships and aircraft because that ice will freeze on contact. For example, here's the wing of an aircraft that's been flying through a cloud that had supercooled water in it. Those little cloud particles froze on contact with the wing and formed this rather ugly and poorly aerodynamic shape, making it very difficult for that aircraft to fly. And a large number of accidents and fatalities have arisen from this kind of a problem. The only thing to do is to quickly get out of that condition and help to melt it off, or have some special technology on the wing that will throw off that ice, either by heating or by what's called a, well, it's a rubber thing that can be expanded to actually physically knock off the ice. A boot, it's called a boot in that case. When rhyming forms on a ship, you get supercooled cloud droplets passing over a ship and it rhymes on. That's very dangerous because that'll add mass to the upper part of the ship. And the moment you add too much to that, the ship will then spontaneously turn over and everyone will be lost. So you really have to get the sailors out there chipping away that ice because it has a very dangerous weight to the top of the ship when supercooled water is collecting like that. Here's a case you can see from time to time. Here's a layer of probably altocumulus that's liquid. Then, for some reason, and it's below the freezing point, maybe it's minus 20 Celsius. For some reason, in some area, that liquid has frozen spontaneously, forming snowflakes and they're falling out, leaving a little clear space in the clouds and a little plume of falling snowflakes out of that region. Look for this over the next winter. If you look hard enough, you'll probably find a case or two of this question.